Now we are ready to state the next theorem, and SAFT, special adjoint functor theorem. Yeah, I mean, I'm first going to motivate it. This motivation actually comes from long time ago. All of you understand topological spaces? In topology, we have some good topological spaces. Yeah. So for example, even if you are doing, let's say, topological K-theory, then you need your space to have certain properties. Yeah. Compactness is always a desirable property. If you don't have compactness, then lots of conditions fail. Compact and what is it usually paired with? Hausdorff, compact Hausdorff. So therefore, like suppose we are talking about real numbers. How can we compactify them? Is there a universal way of compactifying real numbers? One-point compactification, yes. However, one-point compactification is not a functorial assignment. It doesn't behave well with respect to maps. Okay, so therefore, people wanted to compactify in a Hausdorff manner, of course, every topological space such that it is a functor. Now, such other compactification process is called stone check compactification. Okay, so the motivation here actually comes from this. So here Check was a topologist and Stone was an algebraist. So their ideas combined in 1930s. Yeah, so very old days. And whatever they did, I'm going to write down some facts about these two categories, category of topological spaces and category of compact Hausdorff spaces. But whatever they did there, the exact same proof actually goes through if you only retain the abstract properties and not worry about the concrete structure. And that is precisely the statement and proof for special adjoint functor theorem. So it's not attributed to anybody, but if we have to attribute it to someone, then it has to be Stone and Check. Okay, so this is Stone Check compactification. So check is a Czech word. So Stone Check compactification. Okay, so this is going to be, because we are talking about adjoint functor theorem, obviously it's going to be an adjoint to one of the normal, like usual functors. What's the usual functor? It's usually called, denoted beta. Okay, so the diagram is like this. We are given K house, compact Hausdorff, and then on the other side we have top. And the functor that we are interested in is the inclusion functor. Now here I will write down the basic properties of these two categories. Yeah, so top and K house are locally small. You agree with that? Because they are concrete categories. So they are locally small. Okay. Then second thing, yeah, top is complete. Yeah, top is complete because product of topological spaces, you have product topology, and equalizers can also be described in topological spaces. You simply take the set theoretic equalizers and topologize them as the induced with respect to induced topology, subspace topology. So equalizers are also good. But not only top is complete, but you also need some properties for K house. And K house is closed under products. In top. Why is that so? Product of compact Hausdorff spaces is again compact Hausdorff. What is that theorem called? Tikhonov's. Very good. Okay, so thanks to Tikhonov, this is closed under products, and if we show that it is also closed under equalizers, then we are through. Right? So, okay, and equalizers, yeah, in K house are simply inclusions of closed subspaces. Okay, equalizers are always inclusions of closed subspaces, and if you take a compact Hausdorff space and take its closed subspace, then it is again compact and Hausdorff. I think I'm making a mistake. Equalizers in top are simply inclusions of closed subspaces, and hence K house is closed under equalizers. Okay. Now there is a third condition as well. So what did we finish proving so far? That top and K house are both complete and both are locally small. Okay. Now one more thing, that K house, I from K house to top, this inclusion functor, it preserves all small limits. Obviously we just saw how to construct them, so it preserves. It's just the same thing. Fourth property, that K house is well powered. I have to describe this, but well powered, it simply means how many monomorphisms can be there with a fixed target compact Hausdorff space up to isomorphism. So every monomorphism to X, yeah, that must factor through one of the subspaces. And how many subspaces can there be? One of the closed subspaces. And how many closed subspaces can there be? Only a set many. So that's this condition. Yeah. So only a set of subobjects, these are called subobjects, subset subobjects. Yeah, I will define them up to isomorphism. Okay. And lastly, okay, now this is something which I need to perhaps define properly, that K house has a co-separator. Okay, separator, I think I gave it as one of the exercises. Yeah, separators, separating family and detecting family. Okay, let me remind you what separating family means. That if there are, I will directly define a co-separator, yeah, i.e. there is an object X in K house such that given any parallel pair y to z of distinct morphisms there is a morphism h from z to x such that hf is not equal to hg. Yeah, so f is not equal to g, then this can be like this separation can be detected by this co-separator. Okay, so K house has a co-separator. Can you guess what it is? If you have studied enough topology? No. Topologize it and complete it. It's the interval. Okay, the interval with usual subspace topology of real numbers. Yeah, so what is this co-separator? It's this, yeah, x is equal to 0, 1, the interval. And this is thanks to Urysohn's lemma. If you read the definition, the statement of Urysohn's lemma, then it precisely states this, that 0, 1 is a co-separator. T3.5. Yeah, compact Hausdorff spaces are T3.5. So Urysohn's lemma states that 0, 1 is a co-separator. Okay, so these are the 5 desirable properties. I will just take some time to explain what well-powered means, and then we can state SAFT and go through the proof. If these conditions happen, then under these conditions, Stone and Check gave a proof that beta exists. And if you follow the same proof abstractly, then it is special adjoint functor theorem. Okay, so let's talk about subobjects for a while. It's simple. Yeah, so given any category C and an object A, say that a monomorphism let's say A1 to A, M1 is less equal this monomorphism M2 if so I mean, think about inclusions of subsets. When do you say that one subset is smaller than the other? So there should be, like, A1 should be smaller than A2. So there should be an inclusion from A1 to A2. Yeah, what does that mean? Which map factors through which one?
The smaller one's inclusion factors through the larger one.
Exactly. If M1 factors through M2. Okay, so this is the ordering. Now this ordering will make it into a pre-order. Yeah, the collection of all such monomorphisms all monos with target A is a pre-order with respect to less than or equal to. Yeah, because every object, every monomorphism is less equal itself, then if this is less equal this is less equal this, then by transitivity, by composition, transitivity will follow. So transitive and reflexive, but it is not necessarily antisymmetric. Okay, so define sub C of A to be this preorder, to be the Posettal reflection, the partial order reflection of this preorder. Partial order reflection, you understand? I am not saying poset because this may not be a set. Yeah, so just a partial order reflection of this preorder. What do we do normally? We take p comma less equal and then we quotient out by less equal intersection bigger equal. Okay, so sub CA is this particular partial order. Now say that C is well powered if sub CA is a set for each A. Okay, so the power set axiom in set theory, that's similar, yeah? It says this, that the collection of subsets is a set. The category of sets is well powered, correct. Okay. So you understand this, that's all we need. Generally for dualization, yeah, this is the comment which was made by Peter Johnston while teaching this course, that for dual we just add co. Yeah, but we don't want to say the dual of well powered is co-well powered. So we say that well co-powered. Yeah, we just put co at appropriate location. Yeah, we don't want to do it otherwise. Okay. Right, so now we can move ahead and actually state the spatial adjoint functor theorem. Okay, so it says that suppose C and D are complete well powered and locally small. And C and D are let me rephrase, yeah. I just want a minor condition. Suppose C and D are locally small. Further, suppose that D is complete, well powered, and has a co-separating set of objects. Then G preserves limits. G is from D to C, you already know, if and only if G has a left adjoint. Okay, so maybe I should say what is co-separating set of objects here. Yeah, so say that Cj, j in j is a co-separating set of objects for a category A if given any distinct pair there is H from B to Cj for some Cj, for some j, such that HF is not equal to Hg. Okay, so it's just happening for one of the Cj at any given moment. Okay, so that's all. Instead of saying that it's one object, we are saying it's some object from that collection. Okay, as a special adjoint functor theorem, one side we don't have to prove at all. If G preserves, if it has a left adjoint, then it preserves limits. Yeah, we have seen that proof already, irrespective of the hypothesis. So now we just need to show the forward direction. Okay. Now, for any A in object of C, A arrow G is complete, same arguments by lemma 2. Okay, then it is locally small since D is, then well powered since, yeah, sub-objects are precisely coming from C. No, sub-objects are precisely coming from D. Yeah, since D is, yeah, like since, maybe I should write it, since sub-objects in of BF are sub-objects of B. Okay, are certain sub-objects of B, the ones which factor appropriately. Okay, then another thing, if Ci, like I in I, is a co-separating set for D, then what else is a co-separating set? Well, we'll consider this. Then Ci comma F, where I belongs to I and F is any morphism in category C from A to GCI. Yeah, this is a co-separating set. For the arrow category. This is easy to verify, but what we are saying, like we are using that C is locally small here. So we had only a set and now we are taking lots and lots of morphisms which come from A. Like we are taking all possible morphisms from A to GCI. But A to GCI, that's a set, home set in C, that's a set. And we are taking set indexed union of sets, so therefore it is again a set. You understand? So therefore we have obtained a co-separating set, and as before we will call, so I mean we'll start with a new proof essentially. Assume that A is complete. A is the notation for, curly A is the notation for the arrow category now. A is complete, well powered, locally small. With a co-separating set of objects. Okay. Well, whenever we have a set, what do we do with that? To convert it into a single object? Product. We have multiple sets. So therefore, by multiple objects, a set of objects, so we construct a product. So let me call, here it's Cj, J and J. So construct, I'm just going to run through the proof quickly because there isn't much to do here. Construct this product P, which is Cj, J and J, okay, and consider the diagram. Same as general adjoint functor theorem, but we are not going to do all endomorphisms, but instead we are going to use all the sub-objects. So consider this particular diagram, all the sub-objects. And because, this is our diagram, and then this diagram must have a limit. The limit is going to be this I. So this is the diagram, with sub-objects consisting of a set of monomorphisms intersecting each equivalence class. You understand the equivalence class? Less equal, intersection, greater equal. Monomorphisms where they form a set up to less equal, intersection, greater equal. So we are just taking one set because we want to construct a small diagram. Okay. Now we are in a similar situation. Now we have a morphism. Now clearly, all these, you consider any arrow from I to any subobject and then include it into P. Now that particular composition is equal, like whichever subobject you factor through. So clearly the morphism I to P is mono. Do you agree why? Do you see this? Same argument as before. Factorization through limit is unique. So therefore, this must happen. Okay. So, now since any A to P has any morphism from A to P, has at most one extension to a cone over this diagram. We conclude that I to P is the least subobject of P. See, A to P there is at most one extension, because what does it mean to factor through this to form a cone over this diagram? that A must factor, the arrow from A to P must factor through that particular subobject, and it must factor through all subobjects. But I does have that property, so it must be the least subobject. It factors through all subobjects, so it is least subobject. So in particular, what can we say? Any mono I prime to I is an iso. It's a least subobject, so you cannot really go smaller than that. Monomorphism means it's smaller. Therefore, what does it entail? The monomorphism with target I, we always obtain that if we have a parallel pair of morphisms leaving I. So then we construct its equalizer. The equalizer is a mono. But there is no mono apart from isomorphisms. So therefore, home from I to B is at most 1 for each B. Okay. So we have shown the uniqueness property of I to be initial. Now we just have to finish proving that it exists. Okay, good. So now existence of a morphism from I to B. Once we show that, then we are done. Okay. Now construct. So given B, construct another product. But this is a bigger product where J varies over J and F varies over the home set of BCJ. We are taking a massive product, yeah, and define this G from B to Q by declaring, like we always, as we always did in that proof that products and equalizers give all limits, that the appropriate projection composed with G is just F. Oh, sorry. Yeah, F is the component, the index. Yeah, J and F, we are just remembering this F because F already contains the data of J also. Okay, then the one point that we haven't used so far, that it is a co-separating set of objects. So that we haven't used. Then G is monic since Cj is a co-separating set. This is very easy to verify. And now, okay, we just have to define one map from this one massive product to another massive product, and we will be done. Define this by pi jf composed with h equal to pi j. We just remember the jth component. Okay, now construct this pullback and you'll see what's happening. B to Q is monic. We have already argued about that. This is G. This is H. Now you construct this pullback. Let me call this S. Yeah. This is K. This is a pullback. This is L. Okay. Do you remember that pullback of a mono is mono? Have we done this before? pullback is done, like mono is defined in terms of pullback, so therefore pullback of a mono is mono. So since G is mono, L is also a mono. Okay. Right. Then what do we get? So here L is monic, since G is. Okay, now notice something, yeah, just like last one. In the proof of GAFT, we constructed IH as an endomorphism. Here we constructed one subobject of P. What is that subobject? L. Okay, so this L is a subobject. So therefore, I to P must factor through S. Correct? L is a subobject of P. L is a mono. And you look at this diagram. What did we do? We took all the monos, one for each equivalence class. So therefore, from I to the domain of L, there must be a morphism. Okay, so there is a morphism. So by limit property, there is, like the home set from I to S is non-empty. Yeah, that's how I was defined. And therefore, home from I to B is non-empty. End of the proof. You just compose it with K and then you have obtained that there is a morphism. Earlier we showed uniqueness, now we have shown existence, and done. So, so far we have covered half of the course. In this second half, I'm not going to give you as many proofs. Okay, I will try to give you more ideas, and like the proofs will be left as exercises if you want to do them. Anyway, this is an advanced course, so I don't want to enforce a lot of things. Like adjoint functor theorem, Yoneda lemma, these are important results. Yeah, whenever you are doing a course on category theory, then you shouldn't miss these things. But the rest of the things, like if you are very familiar with these basic concepts, then eventually you can read anything. You are capable of understanding any written material. So with that understanding, now I am going to cover a different kind of topic today, and that has to do with the notion of size. Okay, so in the category of sets, yeah, we have different layers. So imagine that now at the heart of it lies the empty set. Empty set has size 0. Then all one element set, then two element sets, and so on. Then this is the sphere, let's say, if you imagine sphere of countable sets. Then you try to increase the cardinality, and this layered kind of behavior is what we are going to try and capture today with the help of entirely categorical notions. And then we will try to see how much of the category is governed by these inner circles, inner spheres. So for example, like even if you are studying, let's say, this Hilbert spaces, Banach spaces, then also you want to talk about the unit ball. Yeah, the unit ball controls lot of data about the whole space. So this is somewhat similar, but then you have to generate this outside data using the data inside through some mechanism. And the best way to do such a thing is via colimits. So colimits help you to build larger objects, more complex objects using very simple objects. Yeah. So one very simple example. If I am given a set X, yeah, I'll write the title of this later, but given a set X, let P fin X denote the collection of all finite subsets of X. Okay, if I know P fin X, yeah, P fin X, can you write it as a category? Can you describe the categorical structure of this? All finite subsets. Is empty set there?
Yes, sir.
Yes. Then any singleton subset is there. Can you describe the categorical structure? Like, is the power set of X a category?
Yes, sir.
Under inclusion? Yes, correct. So it's a poset. So it's a partially ordered set, and P fin X is a subposet of Px. Yeah, that you understand? Okay. So P fin X is a poset. But this particular poset has a very interesting property. So P fin X comma subset, I mean this poset is a lattice actually. By a lattice I mean that union of any two finite subsets is again finite and intersection of finite subsets is again finite. Yeah, this much you understand. However, we want a slightly weaker property, and hence has the following weaker property. Normally, when you say that a limit exists or a colimit exists, then what do you ask for? That there is a cone which happens to be a limit cone. There is a cone over the diagram through which every other cone factors. There is a cone under the diagram through which every other cone factors. But here we are just going to ask for existence of a cone. That's all. Okay, so let me write the definition. So this is called a directed poset. Okay, a non-empty poset P less equal is directed if every pair of elements of P has a common upper bound. Okay, so we are not asking for the least upper bound, we are just asking for a common upper bound, a much weaker property. So P fin X, every lattice or every joint semi-lattice in particular, that is automatically a directed poset. Another example is natural numbers. Yeah, natural numbers do satisfy this property. So for example, I already wrote this satisfies this following weaker property. So P fin X, any lattice, in particular natural numbers with respect to less than or equal to. Natural numbers have this property that given any two natural numbers, one of them is the maximum. Yeah, so that maximum means it has a common upper bound. Okay, so this is our motivation, but this category is a thin category. Directed poset is a thin, like between any two objects, the home set is either empty or singleton. So we want to generalize it. So now this is the generalization. We say that it's a filtered category. So say that J is a filtered category if for any finite category I, and a diagram D from I to J, D has a cone under it. Okay, so what I am saying is quite easy. I am saying that in a non-empty post set which is directed, yeah, what do we ask for? That binary upper bounds are present. But if you have three elements A, B and C, then there is a common upper bound for A and B. Now call it D. Then D and C also have a common upper bound. So every finite subset of P has a common upper bound. This is the same property we have written in terms of this categorical language, that a category is filtered if for any finite category there is a diagram, there is a cone below it. Yeah, any finite diagram has a cone below it. So equivalently, yeah, J is filtered if the following conditions hold. Yeah, the first one is that we will say that it is non-empty. Then second one is that for any A and B in objects of J, there is a cone in J. And third one, for any parallel pair of morphisms, there is a cone or there is a morphism. Yeah, I mean I can talk about morphism or a cone. Morphism B to C in J such that, I mean let me call it H, such that HF is equal to HG. We are not claiming for any uniqueness or any factorization, we are simply saying that there is a cone under this diagram. Weak co-equalizer is third property, then weak initial object is the first property and weak co-products is the second property. Yeah, without asking for uniqueness, we are just asking for existence. Can you see why these two definitions are equivalent? It's the same proof, yeah, same kind of proof that will work by for showing products and equalizers give you all limits. So here we are saying binary co-products and binary co-equalizers, they will give you all finite co-limits, the weaker version of this statement. Yeah, okay. So category is filtered if this is what happens. Okay. Now we are like, I'm calling this category J for a reason. What do we use this notation for? Diagram, the shape of the diagram. So we say that given a category C, a filtered colimit is a colimit of a diagram D from J to C, where C is filtered, J is filtered. Okay, so any colimit of filtered shape. In particular, filtered colimit, you know one example, natural numbers. Yeah, so natural numbers is a directed set. So directed sets are filtered categories, directed posets are filtered categories, obviously, because you don't have any parallel morphism, so no worry about condition 3. Okay, and when do we say that a category has filtered colimits? If it has filtered colimits of all possible shapes. Yeah, so maybe I should write that. So say that C has filtered colimits if for any filtered J and diagram D admits a colimit. So usually, like, if our category J, filtered category J, doesn't have a like an upper bound, yeah, I mean a directed poset doesn't have an upper bound, then it is usually infinite. If it is finite, then it must have an upper bound, yeah, because everything must come together at some point. Why are directed colimits so special? Yeah, we are going to look at these examples, but filtered colimits or equivalently directed colimits, they have a lot to do with finiteness. Okay, before we go there, like how it relates with finiteness, I would like to give you some statement. Yeah, this is a theorem of a similar nature as products plus equalizers gives you all limits. So if C is a category with finite colimits and filtered colimits, if C is a category, yeah, with filtered colimits, then C is co-complete. Okay, so co-complete means it has got all colimits. So how do you generate all colimits? Using finite colimits and filtered colimits. I will give you, I'm not going to give you a proof, but I will give you a sketch idea. Okay, sketch of why it works. So let us recall what we started with. We said that given any set X, we can construct P fin X, the finite power set. From that finite power set, can you recover X? Yes, how do you do it? Take all singletons. Okay, but what's the problem with all finite subsets anyway? We don't have to focus on singletons. If we take the union, but this union has a special name. It's called directed union, because everything is directed. Yeah, it's going together, they are going in one direction. So that's why it's called directed. So the directed union of P fin X is X. So you can recover X using that idea. Yeah, so can you now view it as a diagram? Yeah, so P fin X to the category of sets, you take the map which takes any finite subset to itself, and then you view it as a diagram, like diagram of shape of P fin X comma subset relation, this poset, this directed poset, and then there is a diagram which takes every subset to itself, and then you take the directed co-limit, yeah, then you will get back X. Okay, so the same idea we can use to prove this thing. So if it has finite colimits, then what else, like what do we have in particular? We want to use the result that we have already proven for showing all colimits exist. What is the result for all colimits? If it has all coproducts, all coproducts and binary coequalizers. Well, binary coequalizers have already been taken care of because it has finite colimits. So finite colimits includes binary coequalizers. So if we can show that it has got all coproducts, then we are done. Okay. But we know that finite coproducts do exist. Okay. So it's enough to show that all coproducts exist. The coproduct of any family AI, I and I exists. How do we do it?
Take the finite power set of this family and for every
Exactly. So we take, note that P fin of I subset is a directed poset. Some people also call it directed set. Yeah, it's a directed poset. So you take, so consider the diagram. What is the diagram? That D from P fin I to C, yeah, where you are taking any I prime and mapping it to the finite coproduct of AIs. Okay, and show that colimit of D is actually isomorphic to the arbitrary coproduct. Okay, simple. Yeah, because this becomes a directed diagram, so filtered diagram, and then you know that the filtered colimits exist. And actually, I mean, this is a by implication, of course. Yeah, I mean, C is a category, then it has finite colimits and filtered colimits if and only if it is co-complete. Obviously, the converse is true. Any questions about this result?
What do we send the morphisms?
The morphisms will be sent to appropriate co-projections. Yeah, if you add one more element to I prime, then you will send it to the co-projection, which should exist. Co-projections, we denote them by nu, letter nu. Yeah. So A embeds inside A direct sum B in abelian groups. Yeah. So the same idea. Any other questions? This is actually a very important piece of category theory. Yeah? Finite, these colimits are very important. Okay, let's stop here.